All right. So are you guys already there?
Yes,
Hello?
sir.
Yes,
Very
sir.
Yes, sir.
good. So do you guys have a question up to this point? Question? Can you guys still follow? Hello? Hello?
Wala pang question, sir.
Okay. So just let me know, okay? So this is the only the part one. So there's another part more for the 7 volts. Because since we don't have space, so we will erase this one case just in case that you guys didn't understand this part, so we can go back on that one right away. Because once we've started the second part, then there's no way that I will be able to go back on this part anymore. Okay, because I will erase the entire uh, page, okay, or background. Anyway, so right here, the voltage drop for the R1, okay, is 24. So 6 times 4 is 24 volts. Okay, VR1. So that is your side step. So finding the I1 and then the VR1. So we have more I2, I3, and then VR2 and VR3. And in here, since we cannot easily identify the value of the voltage that will flow in here, and then that will also flow on the R3, we have to get the potential voltage on this node. Okay, so let's just say that this is node letter A. Okay, so let's say potential voltage. What is the voltage? Okay, uh, of our voltage that is flowing once it passed through this R1. Okay, so of course at this point, you still have 28 volts. Once, but once it passed over this R1, then of course it will now be lesser. Okay, so for us to be able to get the potential voltage in A, let's just see that this one is voltage at point A. So we have to get the 28 volts and then deduct the voltage drop, okay, right here, okay, which is I1 times R1, okay, which is actually already this one, 24 volts. So right here, 28 minus 24. So at point VA, we have here 4 volts. So I'll just write it right here. So we have here 4 volts. So now that we know that there is a voltage that is flowing on R2 and R3, then we can now identify the current that will flow on this path or on this path, okay? By using, of course, the I is equal to V divided by R, okay? So I, R2, so we don't have enough space anymore. There you go. Okay, right here. So I, R2 is equal to V R2 divided by R2. Okay. So in here, we know that the voltage that will flow on our I is, I mean, IR2 is 4 volts. Why? Because they are in parallel with each other. And since they are in parallel with each other, so whatever is the voltage that is flowing on this section will also flow on the other section that is parallel with that part, okay, or with that resistor. So R2 and R3 is parallel with each other, so they only have one common voltage that is flowing with them. So in here, VR2 is also equal to 4 volts. And our R2 here is 2 ohms. So I, R2, is equal to 2 amps. Okay. So this is now our third answer. So we now have the I1, IT, and then the We don't have the I1 yet. Anyway, since IT is already equal to I1, then I1 is equal to 6 amps. So let me just put here I1. Okay. So in here, we already have the IR2 or I2, which is 2 amps. So the next one is IR3. So IR3 is equal to VR3 divided by, bakit umi-slant din ako? IR3 divided by VR3 divided by R3. So VR3 is also 4 volts since they are in parallel. And R3 is 1 amp. I mean 1 ohm. So in here, IR3 is equal to 4 amps. Okay. So solving the VR2 and 3 is already simple since they are parallel with each other. So VR2 and VR3 is already 4. So there you go. So we have the R total, the I total, which is also equal with I1, and the VR1, 24 volts, VR2 and VR3, and then the IR2 and then the IR3. Okay, so there you go. We have now solved the voltage drop across of those resistors and then the current that is flowing on those resistors also. So if we are going to compare this one with this table, so right here, for the total voltage, of course, we have 28 volts since this is our source. We have IT as your 6 amps total current. And then the R total is 4.667, okay, which is the same with our R total. And then for the voltage, for the voltage across R1, okay, we have 24 volts. Okay, and then the voltage drop across R2, we have 4 and 4 volts, which is the same with R3. Okay, so right here. And for the current on the R1, so we have 6 amps, which is also equal with our I total, okay, right here. And then we have 2 amps for the R2, IR2, right here. Okay. 2 amps right here. And then for the R3, we have 4 amps. And then they're given resistance, R1, R2, and R3. And then the parallel value of the R2 and R3. Okay, so there you go. So that's why we have this table. So this is the result of all of those voltage drop and then the current across each resistor. So were you guys able to follow so far? Hello?
Yes, sir.
How about the others?
Yes, sir.
Sir.
Okay. So I'll just ask you guys one by one since we're not going to erase the entire solutions. Okay. So Mr. Bradley. Mr. Dulay, were you able to follow? All right, so I guess he's not around. Miss Erlene Joy. Miss Erlene Joy.
Yes, sir.
So do you have a question so far?
Wala po.
Mr. Aaron Sagibo.
Sir.
Any questions so far regarding with our
None, sir.
solution? So
None, sir.
sorry for our messy solution since I'm not really used to write using a mouse. Anyway, Mr. John Ridge, any questions so far?
Clear, sir. No, wala, sir.
Okay, Mr. Gangas.
Sir, nakakasunod naman po.
Okay, Mr. Salvalion.
Sir, kasunod po.
Mr. Aizel,
No question, sir.
Mr. Samuel,
Okay lang, sir.
Mr. Ursua,
Okay lang, sir.
and Miss Baltazar. Nakamute ka. Anyway, so I think she responded but didn't heard anything. Anyway, so when cutting, let's see, another voltage source on the, let's say, on this side, so just apply Ohm's law, okay? And then you will get this one. All right, so I will now erase that one, and then so here's the let's say filled up by let's say the current, and then or the answers filled up by answers from this raw circuit diagram. Okay, so you can also base it right here. So we have 6 amps, 2 amps, and then 4 amps. So basically, I was talking about the KCL, but without KCL, so you can also use the Ohm's law, which is the easiest way. But yeah, you can use KCL like in here. So we have 6 amps going in, and then of course we have 2 amps and then 4 amps going out. And for the next one, we have here a 7 volts only. So of course we call this one, we shorted this one. Okay, your 28 volt. So let's try to solve for the unknowns. So in here, same. Find I sub 1, I sub 2, I sub 3, VR1, VR2, and VR3. Okay. So as you guys can see right here, we have a flow of current that is going through R3, and then some will go through our R1, and then some will go through our R sub 2. Okay, so the same process. So let's get for the R total. So in here, you can get the R3 plus the value of your R1 and R2, okay, or the parallel of R1 and R2, which will give us a value of 1 ohm plus 4 times 2 divided by 4 plus 2. So in here, we'll get a 1 plus have a result of 6, 2.33. Okay. So while I'm doing this one, so try to solve it also on your own and verify my answers also if I put the correct answer or no. So did we get the same answer? 2.33 for the R total. Anyone who's also verifying my answers?
Sir, tama, sir, 2.33.
So once we're correct with our RT, then you can now proceed with our I total. So I total is equal to V total divided by R total. So V total is 7 volts, okay, and R total is 2.33. So our I total is equal to 3. Okay, it's actually 3.004291845, but I'll just put here 3 since we're only getting the 2 decimals. So we have here 3 amps. Okay, and then from here you can actually already get the VR3, okay, or the IR3. So IT is actually equal with our I3 or IR3 since they are in series with each other. And for the VR3, we can also solve for that one already since we already have the value of I3. So VR3, I3 times R3. So in here we have 3 amps times R3, which is 1 ohm. Okay, so VR3 is equal to 3 volts. So that's the voltage drop across this resistor. And as you guys can see, you can just simply get the current that is flowing on the R2 and R1 if we don't know the voltage of this node, or the potential voltage from this point up to this point. So again, let's just call this one our node A. So if we want to get the voltage at node A, let's just say VA, so we have to get the potential voltage right here. Okay, let's just say this one is VB. So VB minus the voltage drop across this resistor, okay, which is I3 times I3. Wherein our VB is of course still 7 volts, and then our voltage drop across this R3 is this VR3, so 3 volts. So V sub A is equal to 4 volts. All right. So as you guys can see, we have 4 volts here. So I'll just put here 4 volts. So in here, since we already know that the voltage that is passing this parallel section, 4 volts and then 4 volts, then we could now say that VR2 and VR1 is equal to 4 volts. Okay, so now we have already solved the VRs. And for the IR2 and IR3, IR1 and IR2. Okay, IR1 first. Okay, so VR1 divided by R1. So VR1 is 4 volts, and then R1 is 4 ohms. So IR1 is IR1 is equal to 1 amp. And then IR2 is equal to VR2 divided by R2. And VR2 is equal to 4 volts divided by R2, which is 2 ohms. So IR2 is equal to 2 volts. 2 amps, since this one is a current. Oops. There you go. So we now have the IR1, the I1, which is 3 amps, and then the I2, which is 2 ohms, and then the I3, 3 amps, and then I1 is 1 amp. All right, and then the VRs are 3 volts and then 4 volts. So let's see if we have the same. So right here we have voltage drop across R1, which is 4 volts, VR2 is 4, and VR3 is 3 volts. I1 is 1 amp, and I2 is 2 amps, and then I3 is 3 amps. And then the given resistance value, and then the computed result for the R1 and R2, which is 1.33. Why is this 1.33? Yeah. So just this one alone, R1 and R2 is 1.33 plus 1. The total resistance is 2.33. All right. So were you guys able to follow so far?
Yes po.
Yes, sir.
Yes, sir.
So from here, the one that we are now going to do is the superimpose. Okay, we're going to see superimpose those values. So the thing that you need to do is get this one. Okay, so the reason why they are in table is for you to be able to get the comparison. Okay, for us to have an easier superimposing solution. So as you guys can see right here, we have the equation for the 28 volts, and then the a solution for the 28 volts, and the solution for the 7 volts. Okay, and then you will get this one. There you go. So you will get this one as the final value of the circuit. wherein if we have the 28 volts and 7 volts, okay, you will get the result of 20 volts only. Okay, so of course the larger value of voltage will dominate the lesser value of voltage, or they will just be simply deducted to the larger voltage. So we have here the 24 volts for the R1 and then 4 volts for the 7 volts. So 28 volts, it has a voltage drop of 24, and then for the 4 volts, I mean for the 7 volts, it has a voltage drop of 4 volts. And then if you're going to take a look on this one, we have here different symbols. We have positive and negative, and then negative and positive. So in that way, we already know that they are, or those voltage source will not add up with each other, meaning they are opposing each current flow. Okay, so that is why for the uh, let's say 28 volts a while ago, okay, right here, it has a current flowing right here. And then for the 7 volts, we also have a current that is flowing right here. So at this point, of course, okay, so there is one current that will dominate the entire circuit. So in this scenario, 28 volts one, since he has a higher voltage source and of course a current also at the same time. So this 7 volts will just be deducted with our 20 volts, and resulted that we have 20 volts in here, okay, with both batteries. And then for the ER2 and ER3, I mean ER2 only, okay, so we have here a voltage drop of 4 and 4 volts also for the 7 volts. Since they have the same polarity or symbols, positive, positive, and then negative, negative, then they will add up with each other. Okay, so that is the point wherein they intersect with this part. So both of them will go down with this branch or with this node. So that is why the voltage or the current will be added with each other. Okay, so are we clear so far on how did we get this I2 or IR2?
Yes, sir.
Okay. And then for the last one, okay, very good. We have here the 4 volts for the 28 and then 3 volts for the 7 battery. And as you guys can see, they have different symbols. We have positive, negative, and then negative, positive. So in that case, you already know that the other one is opposing the other one. So 4 minus 3 will give you 1 volt. Okay. So how will you know? Where will you start? Is it 3 minus 4 or is it 4 minus 3? So we always have this rule in electricity. So it's always the voltage higher more minus the voltage lower. Okay, so that's how our current flows. Okay, we don't have a current wherein it will be dominated by the lower voltage. And yeah, since of course this will give you negative voltage. And as you guys may all know, a current is always positive or zero only. Well, aside from if it's an AC, then of course you will get a negative values. But since we are only talking about DC, direct current only, that is why we have here DC network analysis. So it's either zero or a positive only. Okay, we don't have zero or negative or positive. Okay. All right. So are we clear so far on how did we get this one?
Yes, sir.
Yes, sir.
All right. So this one
Yes,
is a
sir.
lot easier, I would say, but the solution is maybe a lot longer. Okay, but this one is easier than the other. Anyway, so applying the superimposed voltage figures to the circuit, so the end result looks some things like this. Okay, so we now have a voltage wherein flowing, I mean the current flowing right here and then going down and then going through our 7 volts. Okay, and then here are the combined voltage drop on the resistors. And for the current, so the same process. Okay, so let me just remove this one. All right. So for the current, so we have here 6, 2, 4, and then 1, 2, 3. And yeah, so 6 and then minus 1. So why minus 1? Since, of course, they are different when it comes to flow of current. So this one is going to the right and then the other one is going to the left. So again, higher current will be the dominant symbol, okay, IH in this case, IH minus IL, okay, is equal to your final flow of current. So we have here 6 amps minus 1 amp will give you 5 amps. And then for the I2, so since they are flowing, okay, on the same direction, then 2 plus 2 will give you 4 amps. Okay. And then for the last one, so again, they have a different direction. So whatever is the higher one, then that is the first one. The will be the one who's going to dominate the flow of current. So 4 minus 3 will give you 1 amps. All right. So I guess you guys were able to get this one also, since they are just the same. It's just that voltage plus voltage and then current plus current. So are we clear so far to this point?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
All right, very good. Okay, so once again, applying these superimposed figures to our circuit will give you this final value. So this one will be just an additional voltage source, but we have now here a current that is flowing to this side. Okay, so 5, 4, so 4 plus 1 is equal to 5 amps. So the same with the KCL, okay, or Kirchhoff's law. So we have another example here, so you can always visit this one. Okay, so I have prepared 2, so make sure to visit those 2 because those 2 are the one that I think which will help you most to understand about superposition theorem. All right, so here's the summary. So superposition theorem works only for circuits that are reducible to series parallel combinations. Thus, this theorem is useless for analyzing an unbalanced bridge circuit. Okay, so of course you can determine the voltage and current, but not the power. Okay, and then the needful linearity also means this theorem cannot be applied to circuits where the resistance of a component changes with voltage or current. Okay, meaning if there is a capacitor, inductor, or a diode, then superposition theorem is not applicable. Okay, so in other words, if we only have these 3 components, the voltage source, resistors, and then current source, then yes, superposition theorem is super useful. But if there is another, let's say, component wherein you have capacitor, inductor, and diode, then they are not, or you cannot use this theorem anymore. Okay, so it should be linear only. All right. So if you don't know what is the meaning of linear, then you should search it on the internet. Well, anyway, a 2-minute video will clear your mind about linearity. Okay. So hence, network containing components like lumps, okay, incandescent or gas discharge, or varistors could not be analyzed. All right. So we have here. Okay, so which is similar with linear. So it says here that another prerequisite of superposition theorem is that all components must be bilateral, meaning that they behave the same with electrons flowing in either direction through them. So if we have assumed that it is flowing on this side, okay, so not on the conventional way, then it should give you the same result, okay, regardless of the flow of current that you've chose. So it's either right here or right here or right here. So either of those 2. Okay. And then superposition theorem can also be used when it comes to AC or alternating current. Okay. And also with semiconductor amplifier circuits. So yes, they are also usable. And where sometimes AC is often mixed superimposed with DC. Okay. So again, in using superposition superposition theorem, so Ohm's law is your main computations or your main solutions, okay, to solve for the unknowns. And what else? So in here, of course, that is the main goal of the superposition theorem. So the superposition theorem states that a circuit can be analyzed with only one source of power at a time. Okay, so the corresponding component voltages and currents algebraically added to find out what they will do with all power sources in effect. And to negate all but one power source for analysis, replace any source of voltage, like for example, if it's battery, then replace it with a wire or simply short it. But if it's a current source, then leave it open, okay, or break it. All right. And here are my references. So make sure to check those 3 websites. So the first one that I would recommend is this All About Circuits. Well, either of those two, either of those tutorials point or All About Circuit. And then the third one is just an additional one. Okay, if just in case you wasn't able to understand those 2 references. Okay, so for practices, so maybe you can visit Khan Academy. They provide a lot of examples and then the solutions. Or you can visit some website like quizzes, okay, to test whether you've really understood the point, okay, or what is or how the superposition theorem works. Okay, so yeah, that's it for the module 5. And then later on, we'll discuss the module 6, okay, which is a lot more simpler, again, than Kirchhoff's law and mesh and superposition. So any questions so far?
None, sir.
None, sir.
All right, so if you guys do not
Yes,
have
sir.
any questions more, then let us now proceed to the last module. Okay, so this is already your last module before your midterm exam. So I have already uploaded the PDF of nodal voltage. So download your own copy now so that you can have your own copy. All right.
Sir, super last na yan.
Yes, this is the last one. Okay. So this one is actually the easiest topic, I would say, once you understand everything from the start up to the superposition theorem. Okay, so you will know later on. So we have here nodal voltage analysis. So we have this example wherein we can find the voltage drop using a different nodes, okay, or different nodes approach. So nodal voltage analysis finds the unknown voltage drops around the circuit between different nodes that provide a common connection for 2 or more circuit components. Okay, so in here, so let me just go back with the superposition theorem. So in superposition theorem, you can apply KCL and Ohm's law, basically those 2 fundamentals. And in nodal voltage analysis, the main source of your solution is Kirchhoff's first law. All right, and some Ohm's law. Okay, so in here you have the Kirchhoff's first law, and then we will have this as our basis in solving for the n. Okay, n is our nodes. Okay, we have, let's see, node 1, node 2, node 3, and so on and so forth, depending on how many super nodes you have on that circuit. Well, in this case, so as you guys you'll know, when I say super node, whatever is the node that is connected with most of our components. So you already know that in here, our super node is VB. Okay, so that's our N. So at each node point, so write down Kirchhoff's first law equation. So that's the minimum requirement. So you must have the KCL. So you run this one. So the currents entering a node are exactly equal in value to the currents leaving the node. Okay. So if you still wasn't able to understand this one, then I advise you to go back to the PDF of Kirchhoff's law. Okay. And yeah, so without a further delay, let's now proceed on how did we get this equation using the KCL. So let me just copy this one. Okay, so KCL. So as you guys can see, we have here a current that is flowing, and then another current that is flowing right here. And then it will leave the current at point PB. So in here, we have VA, oops, I1. Okay, I'll just call this one I1 since it's the current in here, and then I2 right here, and then I3. So we have I1s. Oh, this one is positive since it's entering to the node VB. And then we have I2, okay, which is also entering the node VB. And then the last one is negative I3 is equal to 0. All right. And then right here, we can now apply Ohm's law. Okay, but before that, okay, I have to end our meeting now since we don't have enough time anymore. Okay, so sorry for that one. Muntik na naman na hindi ko makita yung oras. Buti na lang nag-blink sa task. So just continue the rest on the part 3. Okay, so I'll end this one now and see you guys on part 3.
Okay, sir.
Jack here. Huh? You accused my friend Jack his first day coming back to school. I can't